Zaczytałem się, proszę Państwa, w książce pod tytułem Planeta wirusów. Czy wirusy sterują życiem na Ziemi? To książka, którą napisał Carl Zimmer. Książka, która zdobyła tytuł mądrej książki roku 2021. To pytanie z podtytułu, czy wirusy sterują życiem na Ziemi, myślę, że po okresie pandemii chyba nikt z nas nie ma wątpliwości, jak na nie odpowiedzieć. A co na ten temat mówi autor? Możemy o tym przekonać się w dzisiejszym odcinku. Marta Trzeciak porozmawia z nim i zapyta o jego książkę, która została nagrodzona w tegorocznej edycji konkursu.
Good morning and good afternoon. It's a huge pleasure for me to meet you and have possibility to talk to you. As probably you know, we will talk about viruses. So let's just start strongly. And could you please tell us what viruses are and if they are alive or not?
Wow, two big questions. Viruses are tiny little packages of genetic material. They're not cells because they don't have a lot of enzymes inside of them doing all sorts of different jobs. They really are just packages of genes, usually in a protein shell. And they go into cells and make the cells make more viruses. So are viruses alive? That depends on what your definition of life is, and scientists do not agree on that. Some scientists argue that to be alive, you have to be able to eat, to grow, to divide on your own, and viruses can't do any of that. Viruses don't have a metabolism, for example. So they'll say viruses are not alive. And other scientists will say that's crazy. Of course, viruses are alive because they do lots of things that only living things do. And most importantly, they evolve. We're looking right now at virus evolution paralyzing the world. We have these new variants and subvariants of the coronavirus. That's virus evolution. So I don't think science yet has a really clear answer to whether viruses are alive or not.
It's also a kind of philosophical question. If it was a philosophical question, would you think they are alive? Like, what's your opinion? Do you find them alive or not?
I think that the question actually points us to the fact that we really don't understand life at all in a fundamental way. We're still waiting for a theory of life in the same way that there was a theory of matter that gave us modern chemistry with elements and atoms and molecules and so on. We don't have a theory like that for life yet. There are people working on it. I don't know if we'll live to see it. But in any case, I just don't think that it's possible to really come down in favor of one side or the other of that debate about viruses until the bigger question of what life is addressed.
Yeah, I agree with you. Although I find them alive a bit. But they are so simple, actually. So what's their origin? Because I know that we as a humankind have at least 3 ideas. What's the origin of viruses?
Yeah, so it could be that viruses have lots of different origins. For example, it could be that some viruses originate because they break loose from host DNA. So maybe you could trace some viruses back to genes that were being carried by animals or bacteria or plants or something like that. So that's one possibility. Another possibility is just that some viruses may have been floating around since the origin of life. when life began, it's possible that instead of there being just cells that had genes inside of them, you could have genetic material just kind of floating around, maybe in ponds or some other environment, and they would be sort of cooperating with each other to make copies of each other. And maybe some of those pieces of genetic material became parasites. In other words, they were able to get other pieces of genetic material to make more of themselves without helping the other way. And so, maybe things like that gave rise to very, very primitive viruses. Again, like this is another one of these questions that we really do not have a good answer for, because we barely understand viruses. There are fewer than 7,000 named species of viruses in the scientific literature, but scientists estimate that there might be potentially trillions of species of viruses. So, it's almost pointless to make really big statements about the deep history of viruses until we at least get our first million virus species, I'd say.
Yes, exactly. So, well, at some point they entered our world, or we entered their world, because maybe they were first, maybe we eukaryotic cells were first here. But we know that there are so many of them. They are just such an abundant type of life, no life form. And what was quite a big surprise for me was that there are so many of them in oceans and in seas, because we usually think about viruses connected with ourselves, like what's inside of our body or in body of animals, or like when we think about phages, we think that they somehow live inside of bacterial cells, etc. Could you say something more about those viruses that live in oceans, in seas, etc.? Because I found this subject really, really interesting.
There was a time, maybe 50, 60 years ago, when a lot of scientists would have thought that the oceans were pretty sterile. It didn't seem likely that viruses could survive floating around in seawater. It just seemed too harsh, and viruses were too delicate. That was truly wrong, and it took a while for scientists to think about the possibility that there were a lot of viruses in the ocean, and it also took a while to develop tools to look for them. And once that came together, scientists started finding a lot of viruses, and you have to bear in mind that the oceans are huge as a habitat compared to dry land, and so if you have a lot of viruses in the ocean, that means that they're going to be a lot. That the ocean viruses are actually going to make up the majority of viruses on Earth, and so. Scientists have estimated that the viruses in the ocean might be, the number of viruses would be 10 to the 31st power. So that's a 1 with 31 zeros added to it. It's on par with stars in the universe. I mean, it's an inconceivable number. But the fact is that there are just lots of things in the ocean for a virus to infect, especially microbes, especially bacteria. The oceans are rife with bacteria, whether they're bacteria at the surface carrying out photosynthesis, or whether they're at the bottom of the ocean where they are feeding on minerals and other chemicals that are being shot out of the crust of the earth. So anywhere that there is a cell, there are viruses to invade them.
Yes, and we said that some of those viruses are actually a specific type of virus, which are phages. Maybe we could say what's the difference between a virus that we usually imagine it, like coronavirus that is now so popular, and the phages, because they are not that much the same.
Well, so when scientists first discovered viruses in the late 1800s, they first actually found them in plants. So plants get viruses. And so scientists in Russia and in the Netherlands showed that there was a tobacco plant disease that was caused by a virus. Then people thought, well, maybe people get viruses. And then it turned out that diseases that were known about for a long time of humans were also caused by viruses. Rabies was an early one that was discovered. Influenza, these sorts of diseases turned out to be caused by human viruses. In World War I, a doctor, a military doctor, was treating patients who had dysentery, which is a bacterial infection. So it's an infection of bacteria in the intestines. And this doctor, last name was Durrell, he figured out that these bacteria were actually themselves being infected by a virus. So, no one had imagined that bacteria could have their own viruses. And so Durrell gave these viruses a name. He called them bacteriophages, which phage means eat in Greek. So these are the eaters of bacteria. And we just shorten that to phage now. So it turns out that, bacteria, all bacteria get viruses. They all get phages, whether they're in the oceans, whether they're in the soil. And you don't just have to have dysentery to have phages inside of your body. You and I both have trillions of phages inside of us right now. When you're perfectly healthy, your body is full of phages. Those phages are infecting your microbiome. So you could have dozens or hundreds of species of phages just in your mouth, feeding on the bacteria that just sit on your teeth. So phages are they're still fundamentally viruses. They're still just, genes that are packaged in a protein shell, but they have a particular host, bacteria. They could be, they're really important in a lot of different ways. One is that they could potentially be an alternative to antibiotics, because you could potentially use phages to kill infectious bacteria. Phage therapy is what the technique is called.
Yeah, we are trying to use them as for therapy, as drugs, but it's not so simple. Why it's not so simple? Just could you tell something about advantages and disadvantages of using phages as a treatment?
Yeah, so ideally, if let's say that you have a wound that's gotten infected, ideally you want to get rid of all the bacteria that are causing that infection. You don't want to get rid of 90% of them and then the 10% just grow back. So, so it is possible to apply phages to a wound and have them infect those bacteria and drive down their numbers, but they may not necessarily get rid of all the bacteria, and so that could be a problem. Another issue is that phages have evolved to be very specific in which bacteria they attack. It's evolution. They just keep evolving to get better at attacking bacteria. The bacteria are evolving as well. So so you would really want to make sure that the phage that you're using to cure an infection is matched to the bacteria that you're trying to work against. And bacteria can also do all sorts of clever things, like they can hide they can basically build shields that they can hide behind. It's hard for the viruses, the phages, to get through. So there are a lot of challenges. I mean, this is an idea that Durrell himself thought about over a century ago, and it's still a work in progress. But there are people walking around today who were cured with phage therapy. There are some success stories, and there are a growing number of success stories. And these are people who couldn't be helped by antibiotics because bacteria have evolved to be resistant to many antibiotics. And so we really have to make phage therapy work, because our antibiotic solution is not working very well anymore.
Yes, so our bodies are actually full of viruses, and they live or not live on the surface of our skin, in our mouth, in our organism. But as well, some of them are invading us, and actually we can get sick, as you said, like influenza or polio or AIDS. All of those diseases are viral. But at some point we also discovered that they can cause disease that we don't connect with viruses, like cancers. Could you say more about those discoveries and what we know right now? What kind of viruses can give us cancer or different diseases connected with tumors?
So roughly a century ago, a few scientists were studying cancers in animals, trying to understand the causes of cancers. And they would often find viruses in the cancer cells. And in some cases, they were the same viruses showing up again and again. And so this concept arose that maybe viruses themselves could cause cancer. This was a difficult idea to really establish. Part of the reason it was difficult is because viruses do cause some cancers, but the majority of cancers have other causes, whether it's smoking or exposure to radiation, and so you have this mixture of causes that you have to sort out. But it is quite clear that maybe I think the current estimates are maybe 20% or so of cancers are caused by viruses in people. Perhaps the best known of these is cervical cancer. Women who develop cervical cancer do so because they were infected with what's called a human papillomavirus. So what happens is that the virus gets into cells, and it has an unusual strategy for making more copies of itself. It speeds up the growth of the cells themselves. So if you have more cells with the virus in it, then you're going to have more viruses. Actually, lots of people have human papillomaviruses. They cause warts. Sometimes they're totally harmless, but in certain situations, such as if they infect cervical cells, there's a possibility that they can get out of control and cause a tumor. This is a really profound discovery, because what it means is that there are some cancers that can be prevented with a vaccine, that you can vaccinate against cancer. And so there is a vaccine for human papillomavirus, and in countries where there has been very high vaccination rates, it looks like the precancerous growths in young women that could lead to cervical cancer are getting less common. So this could be potentially saving many millions of lives.
So vaccines are part of the solution or protection from many viral diseases, but at the same time, it's so difficult to develop vaccines against some viral diseases. Why is it so? Why do we have to take shots of vaccine against influenza every season or every year? Why is it so difficult to develop vaccine for HIV, for example?
The short answer is evolution. So viruses are really good at evolving, and influenza viruses are particularly challenging because they are able to not only do they have a very high mutation rate, but fairly often two different kinds of influenza viruses will infect a cell at the same time, and they'll be able to trade genes with each other. So what comes out are hybrid viruses, and so if you try to design a flu virus, and there are a bunch of different strains floating around, and you're saying, well, I want to make one that's going to be effective in the next flu season, you kind of have to guess. You have to guess, well, which of these strains is going to be the one that's most common in the next flu season. Maybe there'll be a strain that will become most common that you don't even know about yet. Flu vaccines are, I should say, regardless of the strains, are very helpful to prevent severe infection. So even if you do get the flu, if you're vaccinated, you're much less likely to end up to go into the hospital. So that's really important. That's something to remember. But none of us want the flu to begin with. It's not fun to be in bed with the flu for 4 or 5 days. And the fact is that flu vaccines their effectiveness against infection can vary enormously from year to year. It can be as high as 60% effective, low as 20%. So that's an area where scientists still have a lot of work to do, and there are hopes of maybe making a universal flu vaccine that would create a different kind of immunity to influenza, an immunity that would work year after year, so that we wouldn't need those shots every year.
Sometimes we can use this vaccine protection or prophylaxis, and sometimes they are just invading our bodies. But some of the viruses are like part of our own genome, and they are called ERVs.
That's right. ERV is short for endogenous retrovirus. And so retroviruses are a particular kind of virus. They're related to HIV. Endogenous means that they are part of us. They are part of our genome. If you're looking through the human genome, every now and then you'll come across a stretch of DNA that is clearly belongs to a virus. And actually, there are roughly 100,000 of these pieces in our genome, and they make up about 8% of our DNA. Our 20,000 protein-coding genes only make up maybe 1 or 2% of our DNA. So we have a lot of viral DNA inside of us. So we inherited those from our primate ancestors millions of years ago. They got infected with retroviruses, and those retroviruses actually inserted themselves into their genes, and then they ended up passing that down to future generations. This happens very rarely, but over millions of years, it adds up. And there are a few cases in which that viral DNA has actually continued to evolve and become useful to us. For example, the mammal placenta needs a certain kind of protein in order to develop properly. That protein comes from viruses, comes from the ERVs. So if you were to take out all our ERV genes, our species would immediately go extinct.
So they are part of what means to be a human, a mammal as well, because they have some function in our organism. In different situations, they are invading our bodies, but also we humans invade animal habitats, and this is the reason why we have, or part of the reason why we have next endemics, next pandemics, etc. Could you say something more? What's the correlation and connection between destroying natural habitats and environment that are wild or should be wild? What's the connection with possible future epidemics?
So if you look at a lot of our most dangerous viruses, you can trace their origins to animals. So HIV is a great example. HIV originated in chimpanzees and monkeys. And we can see evidence of how it was able to jump the species barrier and then spread among humans exactly at a point when European countries were colonizing and exploiting Central Africa, harvesting timber, putting in railroad lines and so on, and disrupting forests and coming in and increasing contact with wildlife and affording viruses the opportunity not only to jump to humans, but then to go from humans to humans. So HIV is one of these examples, and that probably happened in the early 1900s. And now more recently, we can see that when you have let's take influenza. So influenza ultimately comes from birds. Birds have lots of different kinds of influenza. It tends not to be that bad for them, but every now and then it jumps over into other mammals or people and can cause pandemics. We have these gigantic industrialized poultry operations, pig farms, where it's really, really easy for viruses to go from bird to bird, and then every now and then jump into humans. So we just need to acknowledge that this is where new viruses come from, and to just find much healthier ways of sharing the planet with these animals that have lots of viruses in them.
Yes, that this is all connected, actually. So it is said that we can expect every new pandemic every 10 years or epidemic because of this invasion of natural habitats and natural environments. And we see experts saying about this a lot, and still public doesn't seem to be very much interested. Do you think that science doesn't have important place in society or in public discussion? We have this tendency that in media, scientists go together with people who believe in flat Earth, that you have this false balance, etc. What's your opinion about this? And maybe you have some ideas how to solve this problem.
I think it's a very hard problem. I don't have any easy answers. And I think a lot of it connects to our psychology. It can be sometimes very difficult for us to recognize the value of efforts and investments that don't have immediate payoffs. Scientists have been warning about pandemics, the kind that we're dealing with now, since the 1980s and 1990s. They have been forecasting this kind of thing happening. And there's been a little bit of attention to it, but, clearly not enough. And so, this pandemic alone, we don't know how the full economic cost that it'll be because we're still in the pandemic, but it's clear that it's going to be in the trillions of dollars. So this one virus, SARS-CoV-2, has cost human society trillions of dollars that could have been spent in all sorts of useful ways, dealing with poverty and so on. We lost it because of this virus. So if we had spent, let's say a few $1 billion a year on things like surveillance, on developing more effective vaccines, we might have fended this off. It only, the cost for vaccinating the world against SARS-CoV-2 has been estimated maybe in the tens of billions. That is a tiny fraction of the economic toll that this one virus has caused. And so, what happens if we have another virus that brings us trillions of dollars in costs? And, it's frustrating because, scientists have been laying it out. Journalists like myself have been reporting on these things for years. But, when politicians are just trying to deal with immediate demands, do we fix the roads? How many police do we put on the streets and so on? Saying like, oh yeah, we also need a few $1 billion for a pandemic that hasn't come yet. That's something that people just sort of say, oh, well, we'll deal with that later. And so we've kept saying we'll deal with it later, for years now. And now we're paying a terrible cost for it, not just economically, but with, perhaps 15 million lives lost so far.
And what do you think will be the future of this pandemic? We have some reports about coronavirus mutating in wild deer's populations, and we have opinions like we cannot vaccinate all of those animals, etc. It's mutating not only in humans. What do you think will be the future of all of this?
Probably a lot like influenza. Influenza is very common in birds, and it can move from birds back into people. It also gets into pigs and some other mammals. So I don't think anybody is, it's been clear for a long time with influenza that there was no way we were going to eradicate it. We eradicated smallpox, but that was only because smallpox only infects humans, and the way it spreads from person to person, you can actually use quarantines and vaccines and other methods to stop its spread. It would be nice if SARS-CoV-2 had been like smallpox in that regard, but it turns out to be more like influenza. As you say, it's in deer, it's in lots of mammals, hamsters, mink. It doesn't seem to spill back into people that often, but it doesn't take very often to start up a new resurgence of this. So I don't see SARS-CoV-2 going away anytime soon, which is really disheartening because, right now, the vaccines we have are really effective at preventing hospitalizations and death. But it does look like, especially for old people, that boosters will be required. And on top of that, we're still coming to terms with what the toll of long COVID is. In other words, people who recover from COVID, even mild COVID, can end up with lots of different long-running symptoms. There are even, studies, that indicate, risk of various kinds of heart disease in the year after getting COVID goes up. It can affect some people's brains just structurally. What those long-term consequences are, we don't know. And the fact is that probably everybody is going to get COVID, and we're just going to have to watch this experiment play out, unfortunately.
So how do you think, how should we react right now? Do you think that we should have another lockdowns? How we should react to avoid the worst scenario?
I think there are a lot of things that we could be doing to reduce infections that would not actually be that big of an inconvenience. We have known for decades, for example, that ultraviolet lamps are really effective at wiping viruses out. Now, obviously, you don't want to be staring at an ultraviolet lamp, but if you have ultraviolet lamps pointing upwards in a room and you have ventilation to circulate viruses, you can knock out most of the viruses in a room. That costs money, but not a lot of money. And, really, like, you would not notice if you were in a room with that kind of UV protection. You wouldn't be aware of it pretty much at all. That would, I think that would be a great thing to have in schools and churches and all sorts of places. So there are lots of things that we could be doing like that if we were really committed to long-term investment in our own health. Why we're not doing it, I don't know.
Yeah, there are so many viruses on Earth and in our bodies. Do you believe there might be some in outer space? Like, for example, we know there are so many phages in our ocean, and we know that there is, let's say, Europe that might have huge ocean. Maybe it's very different from our ocean, but do you think there is a chance that there are some cosmic phages over there? And what would be your reaction for that?
Well, if there's life on other planets, I bet there are viruses. If there's anything like life on Earth, then it's just too easy to make a living as a virus.
And are you working right now on your new book? Because I know that you've been working about this Ages of Life, but is there a new one coming? Could you say something about this? So after Planet of Viruses, I also wrote a book called Life's Edge, which has been out for a little while now. I'm still working mostly on the pandemic, reporting for the New York Times. I'm thinking about, like, if there is a book that I could write that has to do with the pandemic. That I'm still exploring some possibilities. There are some really important books that are coming out now by writers like David Quammen, and so there's a sort of a COVID literature that's starting to emerge, and I'm just trying to figure out if there's something I can add to it. So I hope it will be published in Poland as well. If not, then I will just read the original, because I really liked the one about the viruses. So thank you so much for this conversation and for your time. And once again, congratulations for winning the award. It was a huge pleasure for me. Thank you very much.
Thank you. Thank you so much.
Proszę Państwa, przenieśliśmy się przez świat wirusów. One prawdopodobnie były na świecie przed nami, ale nie mamy pewności. Może my byliśmy pierwsi, może wywodzą się z naszego własnego genotypu. Tak czy inaczej otaczają nas, są na całym świecie, w naszych ciałach, w oceanach jest ich cała masa. Staramy się jakoś przed nimi bronić, tymi patogennymi, za pomocą szczepień i zastanawiamy się, czy jakieś wirusy żyją, a może nie żyją, skoro nie wiadomo, czy to życie w kosmosie. Dziękuję Państwu bardzo serdecznie za wysłuchanie i obejrzenie tej rozmowy i do zobaczenia w następnych pasmach.
No tak, proszę Państwa, zatem ja wracam do lektury i Państwa też do tego zachęcam.